would love to introduce our guest speaker for today's virtual talk, Adam Hacker, Director of Geoscience at Milestone Carbon. Adam is a world-class petrophysicist who dabbles in geophysics occasionally with some dangerous results, but that's a story for another time. And if you didn't know, Milestone Carbon is a company focused on developing carbon sequestration sites. Adam, we're so happy to have you on today for today's talk. I heard that there is a special hidden talent that you have pertaining to a particular country. So I would love for you to kind of share that hidden talent with us, if you will.
Yeah, no, I speak Japanese. I've been there 3 times. Not fluently. It's really hard to get fluent when you live in not that country, but
Fair
do my
enough,
best.
fair enough. I have a quick little question for you. Is there any way that you can say microseismic is awesome in Japanese?
Ah, yeah. Microseismic wa sugoi desu.
Perfect. You'll have to teach me one day. That's awesome. Well, with that, let's get started on today's topic. It is CCUS rock physics, same as regular rock physics, but new and shiny. So, Adam, please take it away.
Yeah. Good morning, everyone. Thank you for coming to the webinar. As Jordan said, the talk is CCS rock physics, same as regular rock physics, but new and shiny. I am Adam Hacker, Director of Geoscience for Milestone Carbon. Uh, and this talk is not meant to teach you every possible thing you ever want to know about rock physics. It probably won't even teach you 10% of what you probably should know about rock physics. So if you want to know more about rock physics, go buy the Bible of Rock Physics, which was written by Gary Mavko. And it's on its 3rd edition now. It's an excellent book. Mine is getting pretty dog-eared at this point. I think I have the 2nd edition, but definitely recommend this book. It has pretty much everything in it. Also, it's a wonderful reference. So let's move on. So today we're going to talk about carbon capture, sequestration. We're going to talk about rock physics. We're going to talk about a little bit of petrophysics. But what is carbon capture? Well, carbon capture, in a nutshell, is hydrocarbons take thousands of years to millions of years to migrate from a source to a reservoir rock, where we extract them in an industrial timescale, like 10 years, give or take. 10, 20 years. We have some wells, of course, that are older, stripper wells. CCUS is the opposite. We're taking gas from industrial sources and we're injecting it, which is as a fluid with like hydrocarbon properties at an industrial time scale. And we'd like it to stay there for millions of years. We'd like it to not come back or ever see it again, for that matter. So this is a quote by Dr. Alex Bump from the BEG. He's one of the good scientists in this field. Definitely look him up if you have some questions. All right. And why do we care about this? Why is CO2 a problem? Well, the world emits about 40 billion tons. It's a bit tricky to get an exact number because quantifying exactly how much CO2 is coming out of all the cars in the world is a bit of a problem. But most of the CO2 comes from energy, about 73%. It comes from energy and industrial use, transportation, like planes and cars. It comes from the air conditioner in this building. And then the rest comes from things like cows farting and various other chemical reactions that we have. And where do these emissions come from? Well, most of them come from the European Union, the United States, China, and other parts of Asia like Saudi Arabia, South Korea. And if India ever fully develops, I expect we'll see another 10 to 20 billion tons. You can see it's a small piece of the pie currently. And so which countries are currently combating this? Well, all of the ones on here, but primarily the European Union and the United States, and then various Asian countries. China has some goals, but so far they're lagging behind a little bit. All right, so I sound a bit like Carl Sagan. I say billions and billions of tons. Let's put this in units we can understand. So 40 billion tons is about 2 TCF per day. and the United States emits about 250 BCF per day of that, so roughly 10 to 15%. For reference, the entire global natural gas production is 125 BCF. So the US emits about twice the amount of CO2 that the entire world produces in natural gas. And then almost all of the CO2, as we said, comes from like 4 different places. And what is a million tons of CO2? We're going to talk about a million tons for a lot in this presentation. And this is kind of the benchmark that people use for CO2 projects. Well, a million tons per year of injection is roughly 52 MMCF per day. So 52 million cubic feet of gas that we're trying to shove into the ground. And also for reference, if you were wondering, because I looked it up, there's only 6 wells in the entire United States that make more gas coming out of the ground than that. They're all owned by Exxon, and they're all in Wyoming. So the most wells in this country, and I'm sure most of you work in petroleum, so you probably see daily production reports from your companies, don't make 52 million cubic feet of natural gas. So that's how much we're trying to shove down a pipe. So this is kind of unusual, and it's kind of a big engineering problem. All right. So as I said, we're having billions and billions and billions of tons. Sound like Carl Sagan's billions of stars. But, we got to tackle this problem at some point, and the governments of the world have basically decided they're going to. And the journey for each of us begins right here, right? Also, interesting point, Carl Sagan started talking about greenhouse gases. There's video of him in front of Congress in 1962, so long time before it was cool. All right. So another question I get a lot is, why don't you just plant some trees, man? Like, why do we have to spend all this money on expensive carbon capture wells? Why don't you just go plant some trees? Well, if you're curious, it takes about 100 square kilometers of forest to capture 1 million tons per year, and it takes about 20 years to grow. So to get that big of a forest, you would need about this much of Denver, most of downtown Houston and the Heights, all of Manhattan, parts of Brooklyn and New Jersey, all of downtown Chicago. And to be honest, the world really just isn't planting trees. In fact, I'm sure we all heard it from our elementary school teachers that the Amazon rainforest was being chopped down. And for the most part, that's still kind of true. In fact, the Brazilian rainforest is actually carbon positive now. It's no longer carbon negative, which is sad times, but it is what it is. So the world is really not planting trees. We could do that, but you would need a lot of land. It's kind of the same problem with solar. It creates a lot of energy, it needs a lot of land. So we like doing things that are more efficient and use small amounts of land rather than all of Chicago. All right. So what is carbon capture sequestration? How does it work? Well, we have an industrial source, like a power plant here, and it goes to a capture island, usually which involves amine solvent and some other processes. It depends on exactly what's coming out of the power plant. Then we have to compress it, because usually when it comes out of these power plants, it's near atmospheric pressure. So we have to get it up to some injection pressure, usually supercritical. And then we shove it in the ground at a well. Sounds simple, right? And it is, but it's expensive, and it takes a lot of time to do all the engineering on all this, and it takes a lot of time to get all the permits to do all this as well. And how do we make money on this? You might think it's like the underpants gnomes from South Park. Phase 1, collect underpants. Phase 2, ? Phase 3, profit. Sometimes it seems like that in CCUS, but in actuality, we're collecting carbon dioxide, and then we make money via doing transportation and service agreements. This is if like a power company wants to be carbon negative, they'll enter into one of these agreements. Another way that is we get 45Q tax credit from the government. There's also California LCFS credits and other voluntary markets. A lot of the news coming out of projects like Stratos in Ector County, which is owned by Oxy, they're making a lot of money from selling voluntary credits to people like Microsoft and Amazon and a lot of these tech companies. And a lot of these new AI data centers want to be carbon neutral or carbon negative. So you do see a lot of interest in these voluntary credits, and not all credits are created equal. There's a lot more interest in carbon removal credits than carbon offset credits, but yeah, that's a talk for another day. All right. So what is the cost of CO2 projects? Well, most of the cost goes into capture. That amine plant generally costs about $300 to $500 million. So that's a lot of money to bolt on one of those to an aging power plant. So what's really happening is most people are adding them to new build power plants, because why would you put $300 to $500 million into a aging infrastructure that's about to be mothballed? And then you have your pipeline, which is about $5 to $20 per ton. It usually costs between $0 and $50 million for all the pipeline and compression and stuff you need to get it to go into the well. And then basically the sequestration gets whatever's left. It gets the remainder, and it's usually $10 to $40 per ton to build the sequestration well, because we need things like chromium alloy for our tubing. We need testing and monitoring. We have to do a lot of testing, a lot of seismic, a lot of fiber, monitor wells, all sorts of stuff. And we have to pay for financial assurance. And so when you look at the $85 that the government provides, it actually really only works for things that already make CO2 pretty easily. Like ethanol production makes CO2, pure CO2 as a byproduct. All the whiskey people are loving this. Natural gas production as well. That before they were cleaning out their natural gas stream from naturally occurring CO2 and just venting it into the atmosphere. So they just have it. It just doesn't really cost them anything other than these two pieces, the pipeline and the sequestration, to put it into the ground. Things like iron and steel, different kinds of chemical stuff is more difficult because they have to pay more for capture, and it's difficult to get it to be economic right now. So what has happened is we have this huge pie of 40 billion tons, but we're really only attacking like 1% of it. Ethanol production is like 1%, and natural gas processing is like 1%, because that's basically the low-hanging fruit right now. So we'll see how that evolves, but that's kind of the state of play right now. A lot of these projects that are tackling larger, like electrical power, are kind of, some of them are stalled, some of them are going ahead, some of them are kind of demonstration projects. All right, the other thing I get a lot is, this has never been done. Nobody knows if it'll work. It's unproven. Well, that's not true. We've been doing this since 1972. We've got at least 15 historical projects in the US alone. That's not counting any of the ones in like Norway or the EU or Asia or Australia, where we've all done projects. So we've done projects all over the world. And we're currently capturing about 22 million tons per year, which is about 0.4% of our nation's emissions. Remember, we're about 250 BCF. And these are the projects. Most of the historical projects have been related to EOR, because if you're got a lot of CO2, what are you going to do with it? Well, you're going to stick it in the ground for EOR, because that's how you made money before 45Q. The newest ones like Red Trail and ADM are doing permanent sequestration. The other thing you can see from this chart is that we kind of started small and scaled up, and we kind of went big in sometime in the 90s and the 2010s, and then we kind of bounced back to saying about 1 million tons per project is good. So yeah, so CO2 is been done. It's very, the engineering is sound. It is expensive. A lot of these CO2 projects can get up to like $1 billion. So it's not like drilling an oil well where, costs you a little bit of money, but not a ton of money. Some of these projects are very, very capital intensive. And where are these projects happening? Well, generally where we have sedimentary basins. So we have a lot of projects in the Gulf Coast, very close to the coast, generally near industrial corridors like Port Arthur, Baton Rouge. We also have projects in the Illinois Basin, and then there's a cluster in the Williston Basin, and a few scattered around the Rockies, the Permian, and the Fort Worth Basin. It's funny, the ones in the ones in North Dakota are all in the same county, in the same formation, and a few miles apart. And it makes sense. It's where the Indian Car is thickest and most permeable and porous. It's just kind of how geology works. What you don't see is that you don't see any dots in places we don't have basins. Like, you're not going to try to do a sequestration project in Atlanta where there's lots of emissions, but it sits on a granite Piedmont. So not really ideal. California is another interesting case. You have a lot of projects, but it's like all one company. And to do projects in California, you have to own the land, the old oil wells, the emitter, like you have to own everything end to end. So most companies aren't willing to enter into that, except for one. All right. Now we're going to talk about petrophysics of carbon capture, since we've got kind of past the boilerplate, what is carbon capture slides. We're mostly going to talk about brine aquifer sequestration. There are other ways to do things, but they haven't really been scaled up yet. Yeah, we'll talk about that in a second. All right, so when we're in an oil field system, what would we like to have? Well, we'd like to have a trap, a source, a seal, and a reservoir. And the reservoir needs to have porosity, permeability, and a migration pathway so the oil can get up in there, or gas. And then unconventionals, what do we need? Well, we need a source rock, like say the Marcellus. It has to be laterally continuous, which that one is. It has to have enough permeability for the gas to flow once it's fracked, and we have to be able to drill and frack it horizontally. So those are the characteristics we look for when we're looking for oil and gas. When we're looking for a place to put CO2, and there's more than one way to do it, which is, and let's just go through the ways real quick. We have basically EOR, which is what we did from the 1970s and till roughly the 2000s, where we inject CO2 into a depleted oil and gas field, and then we produce the oil and re-inject the CO2. And it just goes in a cycle, and you lose some CO2 every time you inject it. So it does eventually get rid of it. Then we have brine aquifer sequestration, where we inject it down into an aquifer and it kind of floats around and you get some residual trapping. Some people have said that they want to do CO2 injection into depleted fields. And while that seems like a good idea on paper, the logistics are a nightmare and the liability is a nightmare. So there's really no serious projects that are doing this yet outside of academics spitballing. And then we have CO2 into unminable coal. This has actually been done multiple times by the DOE, and it does work. It's just not very scalable. And then we have CO2 into basalt to mineralize. CO2 reacts with serpentine and creates aragonite. This is being done currently in Iceland. The DOE had a test project in Willow Gap, Washington. There's some companies trying to scale this up. I hear there's a project in Oman that's looking to scale this up, and one in East Africa. So this could be promising, but it hasn't yet been scaled or commercialized fully. All right, so what do we need for CO2 sequestration? Well, we need an impermeable seal because we'd like it to stay down there forever. No faults or wellbores that would allow it to leak back to the surface. The salinity has to be 10,000 ppm or greater, because the EPA will not grant any sort of freshwater waivers, even if the freshwater is found at 25,000 feet, as sometimes happens in the Rockies. We need a storage mechanism, so we need to pick one of these as our storage mechanism. And then absorption, solubility, chemical changes can all affect the CO2. And finally, you need the ability to pump it in there. So remember I told you we have to have 51 MMCF per day. Well, that's a lot of gas. So you need the ability for it to go up down the hole and into the formation. All right, so we're going to focus on brine aquifer storage. This is Sleipner, everyone's favorite CCUS example. It's in Norway in the North Sea. They're injecting they've been injecting since the 90s, and it's kind of taken this elongated path. You can actually see it's leaking a little bit out the north end. And yeah, that's going to be, let's kind of go through the equations for brine aquifer storage. So before we do that, we're just going to recap our equations for hydrocarbon storage. Hopefully you guys have seen these once in your life. You have oil in place is equal to your barrels to feet conversion. You have area times height times porosity times 1 minus the water saturation, because we don't want that to be included in our reserves. And then the formation volume factor. Oil and gas is the same way. We have our acre feet conversion, area, height, porosity, 1 minus water saturation, formation volume factor. These last two are the Langer volume equation. So that describes absorbed gas that's absorbed onto the surface of minerals. If you like, you can use Ambrose's equation. This is a very simplistic version, obviously, from I think 1929. There have been some expanded cases over the years. And then we have a dissolved gas in water, because gas does dissolve in water. And if you don't think that's true, go talk to the good people at Coca-Cola. I'm sure they would enlighten you on exactly how much CO2 they can stuff into water. But yeah, so here we have the exact same equation as the first one. We just have a nice little water-oil ratio at the end. So this is what we typically use to calculate oil and gas in place and water in place in reservoirs. So how do we calculate how much CO2 we can stick in the ground? Well, we use this, which is a modified version of the gas in place equation. So because everything in CO2 is done in tons, which is a mass, not a volume, we have to convert from mass to volume. And so basically we have our same acre-feet conversion. This is a density conversion because I like using metric densities. Oh, by the way, everything in CO2 is metric. I guess there was a meeting a long time ago and they decided that they weren't going to use our silly imperial units. But yeah, so whenever you hear like tons, it's always imperial tons. So yeah, we have, let's just go through. We have conversion from acre-feet to cubic feet, conversion from grams per cc to pounds, area times height times porosity times 1 minus irreducible water saturation, because CO2 can only displace about 60% of the water in any rock. The density of CO2, which is an important factor, and the efficiency factor. This is our fudge factor. Petrophysicists always like to throw out a fudge factor so they can easily match things. And then you can use the formation factor. It depends. If you're using the density of CO2 at the reservoir, this is 1. If you want to use the density of CO2 at surface, you can use the formation volume factor, but you can't use both. And then, of course, we convert from pounds to tons because we do things in tons. So that is my modified storage equation. The DOE uses a much simpler one. They just use area times height times porosity times density and times efficiency. And I'm like, no. We got to include our unit fact conversions. Like let's not be silly about this and try to like hide stuff. All right. So when we're talking about saline aquifers, there's a couple things you want to remember. It's generally only possible to use a small portion of the pore space. Why is that? Well, it's full of water, which is an incompressible fluid. So that water is not going anywhere unless you drill a water production well. Because CO2 is less dense, it generally rises to the top of the whatever container it's in. Even supercritical CO2 has about the same density as hydrocarbons. It's generally about 0.6 to 0.8 grams per cc. So it's always going to be less than brine, which is usually about 1.1 grams per cc. And so this is one reason why if you have a big container with like 2,000 feet of 30 Darcy 40% porosity sand, it's all just going to go to the top and you're going to use like almost none of it. And thus even with a volume of plume, only a small percentage of the pores will ever contain CO2, usually less than 5%. All right, so let's talk about open and closed reservoirs. Another thing that we have to consider with CO2, we have to consider in reservoir engineering, is whether the system is open or closed. So some systems like the Permian have these nice continuous formations that go for 100 miles in any direction. They have faults that might cause compartmentalization, but they have no pinch outs that would cause a lateral barrier. And then in the Gulf Coast, it's kind of the opposite. You have a semi-closed system where you have a bunch of sands that were deposited during fluvial events, storm surges, marine. And a lot of them are very discontinuous and isolated. You can try to correlate them from well to well, and you can kind of stand on your head and think, yeah, that might be the same sand. But when you look at it in seismic, they're not really connected. They tend to pinch out and have shale breaks and stuff. So this is important because if the pressure can dissipate to an aquifer system, you can inject more than if you have a closed box where the pressure has nowhere to go. It's basically like Hotel California. And here's an example of a closed system. So in this case, the pressure is allowed to leave the cube that we've designed here. And you see that it basically built spikes at the early time due to relative perm effects, and then it drops. And then we cease injection and it drops again. So this is an example from the Ellenberger in West Texas. And it's actually a good case of why crummy rocks are better than like really porous rocks, because in really porous rocks, it would all just go straight to the top. but since this is kind of a crummy rock, it tends to hit little discontinuities where it arrests. All right, here's an example of a semi-closed system, like Gulf Coast sand. Say we have all these sands stacked on top of each other, and we recomplete or we selectively perforate and try to get it into all these sands that are isolated from each other or partially isolated from each other. Well, what happens is the reservoir pressures up over time. Unlike in our previous case where it spiked initial time and kind of stabilized, these ones continue to pressure up because the reservoir cannot equilibrate to the amount of rate you're putting into it. And this basically translates to an efficiency factor. These guys did a study on efficiency factor, and they found that open systems have much higher efficiency than closed systems. Closed systems generally have less than 1% efficiency. So they have lots of space in places like the Gulf Coast, in places like Port Arthur or Beaumont or Baton Rouge, but they have very low efficiency. So kind of equals out. And then places like Fort Worth, where you have wide open carbonates that are kind of low permeability, low porosity, might have more efficiency. So at the end of the day, you kind of land at the same place. That one thing I liked about this study is they said, how can we increase efficiency? Well, there's a couple ways. You could drill a pressure relief well. That's one. You can make your injection well a horizontal well. That'll give you more surface area, and it'll kind of diffuse it'll also give you a wider area to do your injection. You could wait, basically have longer injection times, lower rate. The last one is cute. You can have horizontal injection well with a horizontal relief well, kind of like a geothermal system. And no one's ever done that, but it's an interesting idea. And they postulated that if you did that horizontal relief well, you could get up to like 20% efficiency. But for our purposes, most open reservoir systems have about 4 to 5% efficiency, and most closed systems like the Gulf Coast have like less than 1% efficiency. Okay, so when we consider areas for CCS, we also need to think about permeability and porosity. So no project can work with no perm and no porosity. But can you do a project with bad permeability and lots of thickness? Yeah, KH kind of evens out. Could you do a porosity with a very low H and very high perm? Yeah, that's like Miocene sands. And so this guy Hoffman plotted all the projects in the world that existed in 2015 at that time, and he kind of showed like there's a continuum here. So we have like Sleipner, which is very high permeability, kind of low H, very high storage, and then you have these ones which failed, like Insula is a famous failure in Africa. What's interesting to me is he kind of put this line of 10 Darcy meters, which is pretty high. I actually think the real line is about 1 to 5 millidarcy feet, or sorry, 1 to 5 Darcy feet, so 5,000 millidarcy feet. And because you see these projects over here, they're like Gorgon. Gorgon didn't fail because of permeability or porosity. It had some sanding issues, so they didn't have any problem getting it in. Anyway, if we think about this another way, so in Texas, we have, Cenozoic sands in the Gulf Coast, very high permeability, very high porosity, generally low thickness, but there's lots of them stacked on top of each other. And then when you get towards kind of the middle of Texas, we have these Mesozoic carbonates like the Austin Chalk, the Edwards Formation, the Rhodessa. And these are kind of medium porosity, medium permeability, medium thickness. And then when you get into like North Texas or like Oklahoma, we have low porosity Paleozoic rocks, low porosity and perm Paleozoic rocks, but they're very thick in some cases, like the Sylvan or the Ellenberger. Or the Viola. So, all of these can work if you have sufficient thickness, as long as you can get it in. All right, how much acreage do we need? Well, if we assume our 4% efficiency, let's assume we have an open system earlier, we can run the previous storage equation backwards and just calculate the number of acres that we need. And what's interesting about this plot is I kind of X'd out this because you can't have 2,000 feet of rock with 30% porosity and 100 like all this good properties and not have it just rise to the surface. So you can't really use this section because if you did, it would just all float to the top. So we have to kind of exit out for buoyancy. But you can see it actually takes less acreage for a thick, low permeability, low porosity rock than a high permeability, high permeability thin rock. This makes sense, right? If you have a 10-foot sand with 2 darcies of perm, it's going to spread out for a long way. If you have 2,000 feet of 1 mil darcy rock, it's not going to spread out very far. So you're kind of turning it on its side. Yeah, but the median is about 5,000 acres. So you need 5 to 10,000 acres per well. And this doesn't account for the pressure space. Alex Bump has given a lot of good talks on how you can have 2 wells that don't have overlapping plumes that then have still communicate with pressure, and that's a problem. All right. So that was kind of petrophysics of CO2. Let's talk about some rock physics of CO2. So can we detect CO2 with 4D seismic? Everybody thinks 4D seismic is the cure-all or the magic bullet for CO2, and that it's not without its merits, but it's also not invincible, or it's like every other measurement. It has limitations. So what does CO2 do to compressional waves? Well, it reduces the seismic velocity. It reduces the bulk modulus vis-a-vis the P wave velocity, creates bite spots and amplitude anomalies. It reduces the frequency. The gas will cause high frequency phase distortions. It causes AVO effects, and it creates shadow zones and transmission effects. Most geophysicists seem to agree that 4D seismic at less than 15% porosity or less than 50 feet is going to be difficult to detect. Here is our plot, Voigt-Rees plot from Mavco Rock Physics book. Remember I told you to buy the book? But, we really need to do modeling on any given case to figure out whether 4D seismic is going to be worth the money, because it costs a lot of money to do 4D seismic. We're talking $3 to $4 million every time we shoot seismic. All right, so one simple way to do this is Gassman's equation, and everybody has their favorite rock fluid substitution equation. So this is not meant to be the answer to all things and everything, but rock physics equations are kind of like Shaley sand equations. Everybody has their favorite, and each one has its own assumptions. But if let's use Gassman's equations for the remainder of this in the isotropic case. And to do that, we need to know, well, what is the bulk density of the gas we're injecting? And luckily, years ago, PhD people decided they were going to test this in the lab. So as pressure increases, the bulk modulus of the gas increases. So you get to like 0.5 gigapascals is about what you see in most reservoirs. And the density stabilizes once it gets into dense supercritical, which is kind of handy. So with those 2 parameters, we can calculate the fluid substitution. And what this is kind of what this looks like in practice. At very low porosities, you're not really getting much difference. And at very high porosities, you're getting a pretty significant change in the velocity or the bulk modulus. So it's much more likely that at higher porosities we can detect stuff than at very low porosities. Stiffer rocks, interestingly, actually create more of a response than compliant rocks, because that change in bulk modulus is seen more. But yeah. And higher pressure, of course, is going to help us because it increases the bulk modulus of the gas. All right, so here's a low porosity case from the Ellenberger. And what you have here is the change in travel time on red and black here. And then this is a synthetic showing what it was when it was brine filled. And then here's the synthetic when it was CO2 filled. So given that the porosity of this is pretty low, the travel time of this is like 45 microseconds per foot. This one's because it's dolomite and it's pretty low porosity. It's like 3% porosity. We don't really expect to see anything, and we don't. So if we injected 60% CO2 into this, as like BKV is doing in Fort Worth, you would not see anything on seismic, essentially, or you would expect to see very, very little response. Perhaps you might get a little bit of a shift, but would it be enough to really pinpoint anything? Maybe not. Conversely, here's a high porosity case. This is the Miocene sand case. I took a well from near Baton Rouge, and you can see there's massive changes in travel time. So the black was the original travel time when it was filled with brine, and the red is the modeled new travel time if we filled all of this with 60% CO2. And you can see on the synthetic too, we're seeing all these changes in amplitude, all these bright spots. So in this case, yeah, of course we see it. So then I kind of said, well, where's the breakover point? And it really is reservoir specific, but yeah, it's the geophysicists are not kind of wrong. We have kind of this area of like plus 30% porosity where it's pretty much a slam dunk. You have kind of this danger zone between 20 and 30% porosity, or 15 to 30% porosity, where yeah, you're getting a change. Is it sufficient enough that you're going to detect it? Probably. I mean, we've seen examples from ADM in Illinois when they only have like 18% porosity, so we're able to see it there. And then you get down to like less than 10%, you're probably not. So the point of this is that you can do fluid substitutions, you can do testing, you can do simulations in software like RockDoc or Trell, or let's see, I think Schlumberger uses is it Olga, and you can test this. And it does vary with salinity, it varies with pressure, it varies with depth. So there is no like one size fits all. This was obviously done in one reservoir. Also, I assume continuous saturation here. If you had kind of a patchy or discontinuous saturation, then it would change. But yeah, so always run full simulation. I mean, that's really where we're going with this. These projects cost lots and lots of money, up to $1 billion. So it's worth the time to go do a full simulation, and rather than just doing some sort of napkin math. And it's best to describe things in total storage per project. Oh yeah, I didn't mention it earlier, but one thing that always annoys me is when people say we can store 500 billion tons in our storage site, and it's better to say per year. You say like we're going to store 2.5 million tons per year at our site. Yeah. So yeah, and you do get an element of choose your own plumes. So, oh, sorry, is it backwards? But yeah, basically do the work, do the modeling. All right. So yeah, most techniques that are applied to oil and gas can be applied to CCUS. Rock physics is not changed from CCUS to oil and gas. Storage equations that work in oil and gas work in CCUS. We just have to change a few things to put it in tons rather than volumes. Nobody ever wants to know how much cubic feet of CO2 you put away, even though you can equate it. The efficiency is more of a function of the boundary conditions than it is of the reservoir properties, although there is a little bit of influence of the reservoir properties. But yeah, if you have a closed box versus an open box, very different efficiency. The fluid substitution techniques we use in oil and gas, there's many of them are very advanced. I showed you a very basic one. Can all be applied to CO2, and you should do it before you go spend $5 million on a seismic shoot somewhere. Also, one thing I didn't mention earlier, these fluid substitution techniques are great for working out permanent seismic arrays. So if you want to put out permanent detector arrays, which a lot of people are doing, you might want to know how many detectors you need. Well, you can use fluid substitution to figure that out. And seismic and acoustic methods probably don't work great at low porosity. They might, you probably will get microseismic events from dilation of fractures, but you're not going to see big change in the bulk modulus at low porosities. And you can test this stuff in the lab. Hell, put it on a triaxial load frame, fill it with CO2, see what it does, and do your simulation. The regulators are going to expect you to have hard like simulation. So yeah. What questions do you guys have?
Thank you so much, Adam. That was wonderful. So insightful. Thank you, thank you, thank you. If you've noticed in the chat that we are accepting questions, everything is anonymous. But if you want to, yes, let's give a round of applause. That was fantastic. Good job. If you want, you can always raise your hand by clicking that raise hand feature. But if you do that, we will be turning on your camera, and then you will unmute yourself, and then you can ask your question. Otherwise, you can simply type it into the chat box. Look at all those applause. Yes, go Adam. Thank you, thank you. It was so great. One question that we do have in the chat here is when pressure relief valves were mentioned, what and to where is that being vented?
Yeah, it's a good question. Essentially you would drill your relief well such that it would only produce brine. So you would, if you have a CO2 plume that's say a mile in radius, right? You might drill your pressure relief well 2 miles away so that it's unlikely to produce any CO2. Now, we all know is once you start drawing down the pressure over here, it's going to pull, kind of skew the gas plume because it's going to want to go towards the low pressure. So a lot of the times, if people are going to do this, they drill multiple ones, like all around the plume. That way, if it does skew it, at least it skews it kind of in both in opposite directions, and maybe it kind of competes with each other. Interestingly enough, Oxy's project in Stratos is doing the opposite. They're injecting water to repel the CO2. They're creating a water curtain well. They have an issue with some existing artificial penetrations they're trying to avoid. So they're creating a positive pressure barrier using water. So it's kind of the opposite.
Next question is, what about CCUS in very low salinity brines, less than 1 kppm?
Yeah, that's essentially illegal in the United States. I'm not sure about Europe or Asia, but the EPA was created in 1975 by Richard Nixon to protect drinking water. That is their only mission. And later in the 90s, it was expanded for air. But they are dead set on not allowing any contamination of drinking water. And it does create an interesting dynamic because, like, in places like the Rockies, you can have drinking water at very deep depths. Like one company that was drilling in the Powder River Basin found drinking water at 18,000 feet. And they were really surprised and kind of disappointed. And the EPA would not grant them an exemption. They're like, no one is ever going to drill this for an aquifer. Like, why would you? You can get, drinking water at 1,000 feet. But they would not grant them an exemption because they think maybe someday we might want to use that to give water to our cities. So
you never know.
Yeah, I mean,
stay tuned.
it is a very rare resource. So.
Next question is, are there any chemical reactions between CO2 in saline aquifers with the components of the rock that could lead to changes in frame modules of the rock?
Oh, yeah, that's a good question. So I didn't have time to go over it, but there are a lot of interactions that happen with the CO2 and the fluid. So the CO2 dissolves for one, and it kind of sinks. So it increases the density of the water. There's some nice videos on YouTube about this. And then it also mineralizes. So you get some creation of aragonite and calcite it takes a little bit of time, depends on how much serpentine or olivine is in the formation. But yeah, you can have precipitation, you can have dissolution of the frame, because CO2 is acidic, so it'll dissolve things. And it's kind of an interesting dynamic because you're dissolving stuff maybe near the well and reprecipitating it over here away from the well, or vice versa. So yeah, it can get very complicated very quickly.
What is required to ensure caprock strength integrity over the life of a project? Are multiple caprock levels a requirement if a primary seal is breached?
Most people do list secondary seals. There's a lot of data that's required to show caprock integrity over the life of the project. You are required to do a mini frac on it to test the frac gradient. You're required to take things like capillary pressure measurements, permeability measurements, relative permeability measurements if you can, if it has sufficient permeability. We basically do a full gamut of core testing and rock mechanics testing, uh, as well as forward modeling and simulation. So we essentially science the heck out of it.
When injecting into an open system, did you mention that a not so great reservoir rock is better?
It is.
Um, and and how does that relate to an efficiency factor if it's poor quality rock? Could you expand on that?
Yeah. So the efficiency factor, even in low permeability, low porosity rock, is still like a couple of percent, like let's say 3%. And it does vary by formation. You can test it in the lab. Um, but then any closed system, like a closed sandbar, is always going to have less than 1% efficiency. So if you have 3,000 feet of 5 millidarcy rock with, say, 5% porosity, you can store a lot more gas in a lot less area than you can in that 10-foot sandbar that's closed, because that sandbar is going to pressure up. You're going to hit your frac gradient of your seal, which you're not allowed to exceed, and then you're going to have to stop, and you're not going to be able to inject anymore. So in terms of total storage, in terms of amount of time you can store, and in terms of area usage and efficiency, it's all better. Yeah, it's funny to think that crummy rock is better than good rock, but it is.
Yeah, absolutely. It threw me for a loop. Can you speak to the industry's interest in the US in CO2 storage in basalts?
Oh yeah, there's a couple startups that are working on it. Obviously, most of the CO2 projects we're doing are in sedimentary basins right now. And there's lots of places in the US that are not in sedimentary basins, like New York City. So we would like to have options for places that are away from sedimentary basins. The Essentially the process is they put CO2 in water and they inject the water down a well, and then the water and CO2 go into the basalt and dissolve any scale, and then it reprecipitates as a aragonite very quickly, generally within like 100 days, 100 to 200 days. Uh, in Iceland, they're doing about, I think, 10,000 tons a year at the Helshidi site. There's a project in East Africa that's coming up. It's supposed to be higher than that, and there's a project in Oman supposed to be higher than that. So far, no one has done it at mega scale, like 1 million tons or even 100,000 tons. So I think it's an exciting area. We'll see. Hopefully, they can figure it out. The issue, of course, is you're creating scale as you're injecting, and you're maybe fracking the basalt as you're injecting. So you got to just work those problems out.
How many times uh, how many times does a CCS operator do seismic monitoring for 4D purposes?
It really depends on your testing plan. Most people tend to do it every couple of years during injection, and then you continue to do it post injection. So most projects will inject for, say, 10 years or 20 years, and then they stop. And then you still have to keep monitoring it because that CO2 plume has continued to spread over time. So we in the U.S. we monitor it for 50 years after the end of
Mm.
injection. So every few years till the end of injection. Eventually, things start to stabilize. Like you start changing like less than 1% per decade.
Hmm.
You don't really need to do that much seismic anymore. But
Yeah.
yeah, that's kind of the lay of the land. Most people are doing
Why the 50-year time set?
that. I guess that's just kind of what the EPA decided.
All right.
I'm not really
And
sure the
what they
good reason.
decided is what goes.
Yeah, I mean it long. I think the idea is it's long enough to make sure the plume is stabilized because it usually takes 10 to 20 years to fully stabilize.
Well, we're almost to the end of our time here. We have a few questions left, so let's see how many more we can get through. So, next question is, which topics do you think would be worthwhile to investigate or experiment on regarding CCUS and rock physics, where academia could focus to contribute to the understanding of CO2 injection and storage?
I mean, there's loads of topics. The Like we showed, doing more detailed testing on different cases for properties of CO2 gases would be useful. So there's a lot of literature on pure CO2, right? Like if I have 100% CO2 gas, what is the bulk density of that gas? Very well known. What happens if it's like 60% CO2 and 40% nitrogen? Well, you can do some mixing laws and try to estimate it, but it'd be nice to do some testing on that kind of stuff. I'm trying to think. There's loads of research. I mean, I would say doing more analysis on released data sets like Sleipner and ADM in Illinois with kind of rock physics simulations would be helpful. I mean, if you search CCS in like Google or Google Scholar, there's like 200,000 papers published every year, it seems like, on this. So you can't keep up with all the papers being published. I'm sure somebody somewhere is doing exactly what I just described already, and they're like, "How come you didn't read my paper?" I'm like, I'm sorry, there's a lot of papers to read.
Someone get AI in on this. Do you do any custom core testing and fluid testing compared to oil and gas?
Yes, we do. We do a lot of supercritical CO2 testing, which is unusual in oil and gas, because why would you? We do a lot of the same testing too, but once we do routine core analysis, we generally do CO2 soak experiments and CO2 relative permeability experiments, which I would think would be pretty unusual in an oil and gas project.
We have two more questions here, and then we'll wrap up. Does oh gosh, I'm so horrible with Roman numbers. Does class 6 require time-lapse carbon dioxide monitoring with pulsed neutron logging?
Yes, it does.
Okay.
Almost all projects incorporate that. You can, there's a whole other talk, there's some great papers by Rob at Schlumberger and Luis Quintero at Halliburton with great details on that. So go to SPWA or One Petro, you can find those papers.
Perfect. Last question here. What CO2 storage projects is microseismic involved in doing characterization, monitoring, etc. for?
I'm not entirely certain what Microseismic Inc. is involved in or not involved in. They don't tell me. But I will say a lot of projects are looking at microseismic monitoring for CCUS. There's some wonderful data that came out of the ShellQuest project in Canada talking about microseismic over time and how to relate it to plume growth. So go look up ShellQuest.
Fantastic. Well, Adam, thank you again so much for your time, your presentation. It's been absolutely amazing. One more time, let's give him a big round of applause if you can find that reaction in your top toolbar there. Thank you so much. Absolutely incredible. So if you have more questions, please contact our team. We'll be sure to send those questions over to Adam and get them all answered. We appreciate you joining us today. It's been a fantastic virtual program. Next time we are doing our virtual talk is April 24th. We're going to discuss Argentina's, I hope I don't butcher this, Vaca Muerta shale with Bill Van Gotten. Energizing tomorrow's virtual talk, This Cow Isn't Dead. If you want to sign up for that, all you have to do is take out that phone one more time, scan this QR code, sign up, and you're good to go. How'd I do, Adam? Did I butcher the name of that shale play?
You did pretty good. At the end, it's Vaca Muerta, yeah, the dead cow.
We'll work on it. We'll work on it. In our next virtual talk, we're going to discuss how we can apply its key principles to enhance domestic hydrocarbon production. You want to learn more? Go online, microseismic.com. Thank you so much for joining us. Have a wonderful rest of your day, night, wherever you are. Thank you so much for joining.